So this week, the math department is having a visitor come in. You may have seen those posters all around that talk about how quantum computing is going to kill Bitcoin and break the internet and what you can do about it or whatever. So that talk is on Friday at 5. So it sounds really interesting, like kind of gloom and doom, but I don't know. Maybe there's some number theoretic solutions or something like that. I think it has to do with public key cryptography and things like that. So I don't know if you're interested in cryptography, but that course is happening in the spring. And I think after this course, you're able to take that course. I know students talk about cryptography and really like it. So anyway, so that might be a nice little intro to that. And I think that guy is also giving a math club talk on Wednesday at 5, and there's pizza. And that talk, of course, would be aimed more towards undergraduates. So it might be, I don't know. So when you go listen to a math talk, if you can follow like the first 10 minutes, you're doing really good. So that's kind of like of course, this I think is aimed more towards, I think the talk on Friday is aimed for a general audience. So he'll probably have some really interesting things to say. So anyway, so if you're interested in that, you can see those flyers around. I don't know where that talk is going to be. It might be in 101 downstairs, or it might be, sometimes they do them over in the, what's the name of that building now? It used to be North Murray. No, not Noble. Do you know where the talk is on Friday? Maybe you don't know.
For the
Quantum something or other, yeah.
Oh my gosh.
Well, there's a poster on the hall. Just as you walk out the hall, you can just look and see where it is. But yeah, anyway, I was just trying to tell people about that because I think that would be really cool. So
Well, there's another one
Wednesday
that's
at 5.
it's at 5:30.
5:30.
It's for the math club, but the talk is really cool.
Yeah, I thought that one said number theory, the title. Something about number theory, something or other. So, and number theory is super fun. So that's another course I think you'll be able to take after this course is number theory. If you like the modular arithmetic stuff that we were doing, like number theory is more of that kind of thing. And stuff with primes and stuff like that. So
Yeah, that's what I thought. Social sciences and humanities.
that's what I was thinking. I was like, it's like, because it used to be North Murray. I don't know what the name of it is now. Yeah.
Well,
So
it's not North, it was what was formerly Murray.
formerly Murray.
There's two, right? Yeah.
Right.
035. So it's in the basement big auditorium.
Okay.
And then Wednesday's talk is at 5:30 in 101 downstairs in this building.
And there's pizza.
There's pizza and it's taxi cabs and subs of 2 cubes and excursion and number theory.
Oh, fun. So I wonder if he's going to do taxi cab geometry. That's kind of fun. Yeah.
I'm imagining so.
Yeah. All right. So today we are just going to talk more about ring stuff. And I just wanted you to be aware we are running out of semester here. And so I was trying to put a third exam on the calendar. Obviously I can't do that during dead week. And so the third exam is going to fall on the 19th, which is the Friday before Thanksgiving, which is good because then you don't do anything over Thanksgiving for this class, which will be kind of a nice break. And also, well, I guess I do have to grade exams, but that won't take that long. So yeah, so that would be on the 19th. So you can put that on your calendar. And I'm sure that that's terrible for you because you probably have a bunch of other exams on that same day. But anyway, that's what we're gonna do.
We like the 174 too.
We could do, yeah, well, you know,
Two
2 parts. Yeah, I mean, like, I felt like this last exam, we didn't really need to do that, you know? It was like, y'all took 30 minutes on the first part and 30 minutes on the second part. So it was almost like, why did we split it into 2 days? I think we probably won't split it into 2 days. I'll just make the exam to where we can do it all in one day.
Splitting it into 2 days would kind of relieve the stress because you could then just focus on memorizing and then focus on learning how to do the proofs.
You
I
liked
liked
it.
it,
You liked
yeah.
it. Okay. Well, that's good. It just uses a lot of class time. And we're supposed to get through chapter 4, and I think that's not gonna happen. So, but the other thing about this class, you know, this class is a prerequisite for a lot of other classes. But the reason is more for the intro to proof stuff. You know, for being able to prove and kind of get familiar with abstract mathematics and And less about like covering a certain amount of content. So, so you shouldn't feel like if we don't get through chapter 4 that, you know, we failed and you haven't learned anything and you won't be able to do well in your other classes. Like that's, I think you shouldn't come away with that impression. Now it would be cool to get to the end of chapter 4 because it has the fundamental theorem of algebra, which like this is an algebra class. That would be cool, you know, to get to the fundamental theorem. But anyway. All right, so today let's talk more about rings and stuff. So we're gonna go to oh, Brandon, I've got your, and Alex, I've got your test. One less thing to read out, carry around. There you go. I do. Yep. Okay, so let me define a couple of things real quick, and I think these definitions won't be super surprising, but we'll write this down so we can use them. What do we mean by something like a to the n? Well, what we're going to mean by that is a times a times a times a. And what we mean by this is n factors. So if we have n a's multiplied together, we'll call that a to the n. And if we mean n a, what does that mean? Well, that's a plus a n times. Okay, and so that's not that surprising. And if we have negative NA, what does that mean? That's negative A plus negative A plus negative A n times. And I'm not going to prove this right now, but from these definitions, that a to the n plus m is equal to a to the n plus times a to the m.
Is that like summer?
Some ands, yeah, some ands. That's what you call the little things that are visible. Yeah, sum together. And then these guys, if they're multiplied together, they're called factors. So we're used to that, saying that a lot, but we don't always say the word some ands very often. Okay, so we have this, and then if we have a to the n to the m, that's equal to a to the n times m. And these can be verified just by using this definition here. Okay, so it's pretty fast. So I'm not going to go through that because you've done this before probably. And I feel like I talk about this all the time when I'm tutoring in the lab. You know, okay, why is this true? Because they're always like, do you add them or multiply them? And I'm like, well, let's try an example. Make up something. So, yep. So those power exponential rules. Okay, so here's another example. So we have a and b and r. Then if we have a plus b squared, well, what does that equal? So let's use our properties here. Well, what does this mean? This means from that definition over there that it's going to be a plus b times a plus b, right? And then I can use my distributive property to distribute that a plus b across those two terms. So I'm going to have a plus b times a plus a plus b times b. And then I can use distributive property again to distribute this a across there and this b across there. So we're going to get a squared plus ba plus ab plus b squared. And then what? Well, can I combine these two together? I'd have to switch it, right? I'd have to switch it. And can I do that in a general ring? What does the ring have to have? What property? To do this. switch them. That, yes, it has to be a commutative ring, right? And so not every ring has the commutative property. So let's just make a note of that. We'll just kind of, we can't combine these. Unless R is commutative. And if you'll remember, commutativity of multiplication is not one of the axioms for a general ring. That's a special axiom that happens if it's a commutative ring. Okay. So, so if it's just a general ring, you have to leave it like that. You can't simplify any further. Okay. So, all right, let's talk about units and zero divisors. This is going to be similar to what we talked about before. So these definitions won't be very new to you. So we'll say an element in a ring R with identity is called a unit. So the ring has to have identity to have units, right? So you have to have a multiplicative identity to have multiplicative inverses, right? So an element A in a ring R with identity is called a unit. And basically, if it has a multiplicative inverse, is what we're going to say here. But let's write it out. If there exists some U in R such that AU equals 1R equals UA. In this case, U is called the multiplicative inverse. Of A, and we write U equals A inverse like that. Okay. So let's talk a little bit about what are the units in the ring Z. Are there units in Z? What do you think? Any units in the ring Z?
Think they'll be rational to solve that equation.
Well, so if you're thinking about an element like 2, for instance, right? Its multiplicative inverse would be 1/2. So that one is not, so 2 is not a unit in Z. Are there any numbers that are units in Z? What about 1? Is 1 a unit? Yeah, 1 is a unit. So 1 is a unit because 1 times 1 equals 1. And so its inverse, multiplicative inverse is itself. So we can write that 1 inverse equals 1. In Z, right? Any other units in Z?
The negative one.
-1. Yeah, and what's the multiplicative inverse of -1? -1, yeah, because -1 times -1 is 1. Right? Yep. So -1 needs to be a unit. Oh, I stopped writing my ones like that, okay. I can write negative, or I can write -1 inverse is -1 here in Z. Yeah. So I want us to start thinking more broadly about this notation of this inverse here, right? Because I think when you are doing computations in the real numbers, you think, oh, a negative exponent means I flip it over, right? Why? Because we're using this negative exponent notation to mean the multiplicative inverse, right? And it does happen to be consistent with the exponentiation rules in the real numbers, right? But when we're talking about a general ring, that -1 multiplicative inverse notation might not always mean that you flip it over, okay? So you're gonna have to be a little bit careful. So that -1, we're using power we're using for multiplicative inverse. And so it's gonna be a little bit dependent on the context and what does multiplication mean in a certain ring, okay? So we have to be a little careful there. All right, any other units in Z? That's it. Any zero divisors in Z? No zero divisors in Z? So do you remember when we were talking about rings like Z mod n? What was one of the conclusions that you all had made in Z mod n about units and zero divisors? If an element was a unit, was it a zero divisor? If it was a zero divisor, was it a unit? No. Did it have to be one or the other in Z mod n? Yes, except for 0, right? But here we see in Z that an element like 2 is neither a unit nor a zero divisor, okay? And so one of the things I was seeing, and as I was grading homework, were things like, oh, it's not a unit, therefore it's a zero divisor. And that's true in Z mod n, but that's not true in general. Okay, so here's a little example. So just note, we'll say the element 2 is not a unit, nor is it a zero divisor. So it's neither. It's neither. Okay. So how about this? What are the units in the ring of 2x2 matrices with entries in the real numbers? Okay, and I just had a thought. Colin had emailed me about homework 17. He was having trouble copying and pasting the LaTeX code into Overleaf. Was anyone else having issues with that? Okay, if you would like the LaTeX code for homework 17, just email me and I will add you to share my Overleaf file with you. It may just be the easiest way to do it. So I can share it without giving you editing powers over the file. So maybe I should have been doing that the whole time. I don't know. But yeah, so if you were having troubles, you weren't the only one. So, okay. So what are the units in that ring? Are there units in that ring? What do we mean by units? Now, what kind of multiplication are we doing in that ring? Yeah, we're doing matrix multiplication, right? Yeah. So is it possible to multiply two matrices together and get the identity? What's the, in order to have units, we have to have an identity. We have to have a multiplicative identity. What's our multiplicative identity in the 2x2 matrices? Yep, that's it. So I know my 1R is this matrix, right? That's my identity element, multiplicative identity. Can I make, are there matrices that have a multiplicative inverse with matrix multiplication? Brandon's saying yes. How do you know? Or what do you mean? What are you thinking of?
I kind of remember the exact way to do it. It was like, the reason I know my head is because I know I did it in linear algebra. No, I remember it.
You remember that it's back there somewhere, right? Yeah. Do you remember talking about invertible matrices in linear algebra? And how do we tell if a matrix was invertible or not? Does anyone remember that?
It was symmetrical.
It was symmetrical? Not necessarily that. Yeah. It had to have determinant that was non-zero, right? Was part of it. And why was that? Do you remember how to find the inverse of a matrix? Like if you had a matrix to figure the procedure for figuring out its inverse, remember that from linear algebra?
Isn't there an equation for the 2x2?
There is an equation for the 2x2 and I was about to derive it. Yeah. So what you would do is you would take the matrix and you put it here and then you do you do the identity matrix here and then you row reduce until you got to, remember doing that? Yeah. So you'd start with like A, B, C, D, and then you would do row operations. I did this earlier for fun. Okay, so let's try to get rid of this guy here. So we're going to multiply that matrix by C and that matrix by A, and we'll try to get it. Y'all don't have to copy down all these steps because it's maybe a little tedious. So what, in other words, what I'm doing is I'm doing row 1 goes to C row 1. And row 2 goes to A row 2. Maybe I'll do negative A row 2. How about that? Well, just A row 2. We'll do A row 2. And then I'll subtract them. Okay, so I have CA, CD, C, 0. AC, CA. Well, so this is, I did the real numbers, which is, it's, what am I trying to say? The real numbers are commutative, so I can write this however I want. So we'll do C, D, 0, wait, I think I want AD, yeah, 0A, yeah. And then I want to do row 2 goes to row 2 minus row 1. And so then I'll get AC, BC, C, 0, 0, and then I'll get DA minus CB. And then I'll get negative CA. And then I can do, let's divide row 1 by C so it looks cleaner. So I'll have A, B, 1, 0, and 0, DA minus CB, negative CA. Okay, I just divided by that. Okay, then I could do row 1 goes to, I want to subtract, I want to get rid of, oh wait, no, I want to divide, okay, I want to also divide, I want to make this a 1, right? So I'm going to divide by that guy. So let's make that a 1, and then this is divided by DA minus CB. You see why the determinant needs to be non-zero? Look at that, I'm dividing by that, right? So I've got to have a non-zero determinant, because that bottom thing, AD minus CB, that's the determinant of the matrix, okay? So that's why that's the condition. Okay, and then I want to get rid of that guy. So I'm going to multiply this guy by B and subtract that one, right? And so I'm going to do that. So I get A0, 0, 1, and then I'll have 1 minus BC over AD minus BC. And I'll have negative AB over AD minus BC, and then I'll have negative C over AD BC, and then I'll have A over AD minus BC. Yeah, you can do this on your own sometime. But anyway, we end up with, when you do all the simplification, you get D over AD minus BC, you get negative B over AD minus BC, you get negative C over AD minus BC, and then you get A. And so that is the inverse of the matrix. And you can see where that, you're dividing by that number that is the determinant. So a non-zero determinant is the deciding factor for an invertible matrix, for any, it's not just 2 by 2, any of them. Okay, so matrices in which AD minus BC is non-zero will have a determinant. We'll have a multiplicative inverse. A multiplicative inverse. All right. There's a little bit of linear algebra for your Monday morning.
And it doesn't, so it's in the entries are real numbers, so it's okay that it's fractions.
It's okay, those
Rational.
fractions,
Okay.
yeah, yep, that's the right question to ask. Okay, so let's define zero divisors real quick and talk about those for a minute. Okay. So an element in a ring R. Oh, I need my video here. So first of all, it has to be a non-zero element. Secondly, there exists a non-zero element. Why did I call it C? I don't know. C in R such that AC equals 0 R. Or CA equals 0 R. We don't necessarily have to have commutativity. So if AC equals 0 or R or CA equals 0 R, either way, A is a zero divisor. Okay, so so if a matrix has the, okay, so let's go back to our matrix example in MR. If we have the case that AD minus CB equals 0 R, which 0 R in this case, oh, 0 in the reals, so just 0. So these are real numbers. AD minus BC is 0 in the reals, right? So these are all real numbers. Okay. Then we have that A, B, C, D multiplied by D, negative B, negative CA. Is going to equal to what? So I'll get AD minus BC. I'll get negative AB plus AB. I'll get CD minus CD. And I'll get negative BC plus AD. Right, and so that's 0, that's 0, that's 0, that's 0, so that's 0. Okay. So in the case of these matrices, Oh. If I have AB minus BC is non-zero, I can take the inverse of it. I have multiplied it first. If I have the case that AD minus BC is zero, I can find an element in MR that I can multiply by to get zero, right? It's in this form. So in the matrix ring, every non-zero element is either a zero divisor or a unit. So that's the case in this matrix ring. So we can notice that. So let's say note. We have proven that by those two examples, is either a unit or a zero divisor. So we just showed that. That's kind of an interesting thing. Okay. So we've got like 20 minutes. Let's talk a little bit about Cartesian products because we haven't done a lot with Cartesian products. And there's a theorem, I think it's theorem 3.1 in the section that talks about addition and multiplication in Cartesian products. So let's define what that means, because you will see some Cartesian product stuff. So let's consider the ring Z mod 12 cross Z mod phi. And how is that defined? That's defined to be made up of ordered pairs. And the ordered pairs in the first slot is an element of Z mod 12. And in the second spot is an element of Z mod 5. So the elements of this guy look like this. So we'll say A comma B, such that A is in Z mod 12 and B is in Z mod 5. Okay, so this is so I have a lot of questions about this ring here, okay? So I'm just gonna write down a whole bunch of questions and then I'll let y'all explore and play around with this ring, okay? So the first question is, how many elements are in this ring? So is this a finite ring? If it's finite, how many elements are in the ring? Okay, so that's a question. What else could we ask? We could ask, what is 0? And does it have a 1R? Right? And we can ask what our unit, so let's just do some computations. So let's compute like 7.3 plus 5.3. Oh, let me define and we'll do some computations. I'll tell you what that means in a minute. I haven't defined what those operations are yet, but I'll define those. What else? What are units? So does it have units? If so, what do units look like? So if it has units, what are some of the units? What do they look like? Does it have zero divisors? We could do some equation solving. Let's see if you can solve an equation in this ring. Okay. So So, and let's see if we can find a subring. So can we write down a subring? We may have different ones that we come up with. What's the subring of this ring? Okay, so let me define, so this is actually a theorem in our book, theorem 3.1, which is the definition of what we mean by addition and multiplication. So in a Cartesian product. I should have done this a little earlier, but I didn't. Let me write down the actual statement from the textbook, just so that we're all consistent here and I'm not making up stuff. We'll get I mean, I know what the definition is, I just don't know what the first part of it says. So, okay, so here, let's do this. Let R and S be ring. Okay, define addition and multiplication on I have no idea why this is listed as a theorem. Oh, because it's claiming that the Cartesian product is a ring. Okay, so that's the part that's a theorem. So it's defining addition or multiplication this way. On R cross S by, so we'll have, like, if I have R S plus R1, we'll say R2, let's do subscripts. So if I have R1 S1 plus R2 S2, then I get R1 plus R2 S1 plus S2. I like that better. The book uses primes, but I don't want to use primes. And then if we have R1 S1 times R2 S2, you just multiply the first part. So R1 R2 S1 S2. So what I want you to notice here is this multiplication is a little bit different from, like, you might think about vector multiplication. We have two flavors of vector multiplication, remember? What are two different ways we could multiply vectors? Yeah, dot product and cross product, okay? And so dot product is kind of similar to this, because on dot product, you multiply the first ones and multiply the second ones, but then you add them together and get a scalar output, right? For dot product. And then for cross product, you do this whole thing with the matrix and blah, 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 right? So, and you end up getting another vector, but it's like pointing, you do the right-hand rule and all that. So you get a vector that's perpendicular to both and so on, right? Okay, so this is a different definition of multiplying these kind of ordered pair kind of things. It's different from dot product and cross product. Okay? So this is the definition. So the theorem says then R cross S is a ring. Okay, and so we'd have to verify that, but I'm not going to prove it. And then we can say if both R and S have an identity, then R cross S does. Okay, so that's a theorem. That's the definition of what I mean by multiplication and addition in this ring. Okay, so I'm going to turn you loose. So get with your classmates and friends and try to answer these questions about the ring D mod 12 cross D mod 5. And I would discourage you from making a multiplication table unless you're using, like, Excel or something. You might be able to do this in Excel. Anyway, that could be fun. So, yeah, so talk to your neighbors and see what you can come up with.
Well, it would be the limit, but it would be easier to
Well, there's 12 options, right?
Yeah.
There's 12 options, another child. for each of those 12.
I was just.
So it had a, if we had any.
I mean, isn't
Yeah, that's what I'm
zero,
worried.
so it's
They're all these
zero,
combinations.
12.
What was the
Yeah, that's
zero?
what I'm worried
Zero,
about.
what was zero?
Yeah.
What's the part? The zeros on it. Yeah, I know, yeah. Thank you.
So then.
Are you, the second one, or one, or? you-
Yeah.
Okay, yeah.
We have to think about like. There's multiplying times one, get the same thing, yeah.
Because again, it's that.
And so I think we should write that it's class. Yeah.
Yeah.
More than just like.
I got one. I got, all the threes, I'm like, oh, there's a five, six. And they were like,
Yes.
the cross product actually one, like, the cross product. Or like.
Yes.
Would it be one from a one?
Yeah, so we could have like five, and our,
How close to you and Amanda want to hear, or have you been talking some? I know, just kind of independently working, yeah, flip around there and you'll.
I would say, we could do seven, yes. Oh, we have one right here.
Oh, yeah.
Another, no, wait, there's. Yeah, we don't have these, yeah, that was. I mean, we have one and one.
Yeah, that's true. So,
Should work. I'm like eight by that. Just say one. Trying to think of one that wasn't. Interesting. Yeah. was it simply just.
What if the second component were 0? What if the second component were 0?
But don't zero divisors need a non-zero, like multiplication between two non-zero elements.
Okay, so how does that fit that?
Well, if we have one of our elements being 0.
Okay, what do you mean? Like, give me an example.
Oh, if you're trying to like get two elements from Z mod 5, you just give it 0. We can't really do that without having.
Right.
Z1 because.
But we're not talking about sellers as my 5 by themselves, we're talking about ordered pairs, right?
So is that allowed?
Well, convince yourselves one way or the other.
Yeah, I guess as long as the entire element is not 0, 0. So we can kind of- yeah, so but we can literally just do like 0 and then an element of Z mod 5 that's not 0 and then an element of Z mod 12 that's not 0 is 0. Yeah, and that would always give us our zero divisor and either equal to 0. Yeah. Or even 2, 0 and yeah, 2, 0, 0, comma.
So for Wednesday, we're going to start by presenting some solutions to some of these questions. So what group wants the first 2 bullet points? Y'all want that one? Okay, so this is Brittany, Brandon, and okay. Who wants this one, just computational instead of any other one? You're like, you better raise your hand fast. Austin and Sophie, do y'all want the next one? Units? Or do you want a different one? Take a different one? You want 0 divisors? Okay. So Sophie,
Like the first one.
Austin.
Z mod 12.
Who wants to talk about units? You want units? Okay, so Zach, Dakota, and Alex. Okay. Who wants to do solutions to equation? Anyone find any solutions? William and Seth, did you find any solutions?
We can do that one, or we can do it.
You can do it? Okay. It's okay if you don't find all of them, but just find some and give us what you can. Okay. And then I guess, did I sign y'all? You want to find a subring? Okay. So you can pay me. Yeah, you can find a sub, and you could, there are multiple subrings. So if you can find one, if you find 2, that'd be great. Maybe you could find all of them. I don't know. So, okay, so we'll do that on Wednesday, beginning class. Okay, and we are almost done. So that will be the last bit of 3.2. Then we just have section 3.3. We'll finish Wednesday and Friday, and we'll be done with chapter 3. So the exam will be over chapter 3. So we're going to finish chapter 3 this week. Okay. Chapter 4 will just be on the final. Yep. Which is comprehensive. Yeah, I don't know what the final will look like. I haven't even thought about the final yet, but I'll have information about the final someday. Okay. Sure, of course.
That, like, I feel like I don't understand why it's long.
Yeah, so
I think part of it is I didn't know how to represent very well.
I think that's it. Yes. Right.
So what I was trying to show is that like the multiplication up to K is
Right, so
Is
you
equal
have
to-
these weird subscripts, so I guess what you mean is like you're multiplying A by itself.
Up to K times.
Yeah, but what's the one doing? That's where I was confused. So I wasn't quite sure like what your notation was. meaning
Yeah.
there. You know what I mean?
That-
Like your notation was a little weird. So and then I wasn't clear that like, what are you assuming, you know? So for the induction step, we want to assume that A to the K, oh yeah, so no, here you got it. You're doing your assumption there. And then, and you're also assuming that that A equals B,
Yeah.
right? So you've got two things that you're assuming. So between those two things, you want to put that together. So if you have A to the K equals B to the K and A equals B, then you can multiply, you know, this by A and that by B. Right.
I didn't even consider, yeah, because what I was
Okay.
thinking about doing was showing that A to the K is a bunch of A's multiplied K times.
Uh-huh,
And then showing that that is equal to A to the K times one more A, which is like if we just add one more, and then that is equal to A to the K plus one. And then you can just
right,
say
but there
that-
wasn't really any argumentation about why those should be equal to one another. And the key point that you're missing is that we're also assuming that A equals B.
Yeah. I
Right?
needed to
And
add
so you
that.
gotta have both of those pieces to be able to get it all put together. So it was a combination of not realizing that, and then like the notation was kind of wonky. So,
I think I have the exact same question. I think I did like almost the same thing. I think
yeah,
this is almost the same thing I was having with conduction before, but I'm not sure why. Because when I was writing it, I felt like it seems fine. I just don't.
yeah,
Teacher.
right, yes, okay, so here's what I was expecting, okay, so for the induction step, so your base case is perfect. For the induction step, we want to assume that, so what you did is you assumed that the n plus first case was true, and you kind of went backwards to the nth case, which is not the way induction goes. You assume that I'll use your m, that the A to the m.
Oh.
That A to the m
Why did I do
equals
that?
B to the m.
Why did I do that?
I don't know why you did it backwards. And we also have that a part of our assumption at the beginning was that we had the A is equal to B, right? So if you have those two things, it's not hard to put those two things together and
I was-
get
I don't know,
get
why did I do
go
this
forward.
one?
Yeah, I don't know. It's like it's like you were doing it, but you were kind of going backwards. So it was
Yeah.
just weird.
I guess that isn't really. So, okay, yeah.
Yeah, it was just backwards.
And I had one more question about the homework.
Mhm.
So when it says use theorem 3.1.
Yeah,
Questions?
I meant to be 3.2.
3.2, okay.
Yeah.
Okay, thanks.
Because 3.2 is the one about subrings. 3.1 doesn't make any sense.
Yeah, it was like. cartoon
That's
comics.
not right. And I think I fixed that. You may have printed off or is that the one?
Yeah,
just
it's the
pulled
one
it?
on Canvas.
Oh, gosh. Well, anyway, I fixed it somewhere. Oh, I should have, I need to take a picture of this, who's doing what.
Thanks, Dr. Moss.
Yeah, no problem.